Thank you, Veronica. Thank you all for coming. I'm going to tell you a very, very small amount about some of the math I do, the sort of more respectable math I do, but I'm going to tell you a lot about the visualization, the artwork, and the relations between the mathematics and the artwork. I've got a lot of things to get through, so it'll move pretty fast, but I'm not going to spend much time on any one topic. I'll just show you some interesting images, and then we can ask questions later. And at the end of the talk, I invite you to come and play with all of the work that I've brought with me, and of course I'll be happy to answer any questions. So maybe we could take the lights down just a little bit, just so that the screen's a little bit clearer. So let me first tell you just a little bit about the kind of math that I do. So this is what my mathematics looks like. I spend a lot of time drawing pictures of shapes in 3 dimensions. And so there are some numbers involved, but not many. Maybe this is a little different from most of the mathematics you might imagine people do. I also use a lot of computers. So visualization plus computers are involved. And so it's sort of a natural thing to use those same skills of mathematics and computers to use them to visualize things. So this is sort of a crossover between the two worlds, maybe the closest crossover. So this is a 3D printed sculpture of a knot complement. So what that means is you take a ball of material and you imagine a worm drilling or eating a hole through the ball in the shape of a knot. And this is a kind of 3-manifold that topologists study. And this is a sort of 3D printed visualization of the same thing. So I'm going to go through a whole bunch of different things that I've worked on and just say a couple of words about the mathematics in each one of these things. And then a little later, I'll talk about some sort of maybe philosophical thoughts on what makes a good visualization, what makes a good illustration. So starting out many, many years ago, the platonic solids, there's all kinds of wonderful symmetries involved in these. And of course, you can 3D print these things. And you can 3D print all kinds of things, all kinds of polyhedra. These are the Archimedean polyhedra, slightly more complicated than the platonic solids. And then you can use these shapes as an application. Here are these are the first mass-produced 120-sided dice. So if you ever need a game where you need to choose between 120 possible choices, then these are the dice for you. Again, I've got one of these with me here. You can check it out later. It is possible to tell which number is on the top. That's one of the issues. Here are some other things, other dice in that sort of family. So these are not cubical dice. They're strangely shaped. And so the first question you might ask is, are they fair? And there's an interesting story there. What is it that makes a die fair? And it's to do with the symmetry of the object. So it turns out that actually all of the faces of these dice are the same. So these are fair dice. They're not as symmetrical as the usual cubical dice, but they're still fair. You can do the same thing with dodecahedral dice. So I use 3D printing in my teaching as well. So these are some very large sculptural surfaces that I built. This was for multivariable calculus. There were these standard sort of surfaces that people use, and I made these for Swinburne University of Technology in Melbourne. Had a lot of money left over at the end of their financial year, and so they wanted to spend some money on something that would be useful for their students. And you can see next to them there's these much smaller versions, which are just as effective and much cheaper. So I use these with my students to help them understand these surfaces and what the different cross-sections through them look like. This is another kind of surface, this time with a wordplay element as well. So I've highlighted here on this photograph, maybe you can read the letters S-P-H. So this is a self-referential idea. So this is a sphere that says sphere. The word sphere is tiled over the surface of the sphere. Do you need to? Oh, it's not picking it up. OK. So now I have a second microphone. Here's the same idea, but in the form of a bunny rabbit. And I should mention, a lot of the work that I do is joint with other people. So this is joint work with Craig Kaplan, who's a computer scientist in Canada. And this is a very famous shape. It's called the Stanford bunny, which is this sort of classic example in computer graphics that people use to work on three-dimensional manifolds. Again, maybe you can see here there's the letters B, U, N, N, and Y. So the word bunny is tiled over the surface of the bunny 72 times. So moving on to topology. Topology is one of the main areas I work in, and this is a sequence of ceramic 3D prints. You don't only need to print in plastic, you can also print in many other materials. And so these ceramic prints show the topologist's joke. So the standard joke about topologists is they can't tell the difference between a coffee cup and a donut, because as you can see, you can deform one into the other. So topology is the study of geometric shapes when you don't care about lengths and angles, you only care about connectivity. And I guess I did this in ceramic because it's the right material for a mug. Ideally, the donut would be made out of edible donut, and you would need to have, there are these multi-material printers where you can print in different kinds of material. There is not yet a multi-material printer that will gradate between ceramics and donut, but I'm hoping that one day there will be, so I can do this properly. Other topological ideas, so this is actually a crossover with one of my other interests, which is juggling. So this looks like a braid of 3 strands, but it's also the path through space that 3 balls take as you juggle them. And so if you imagine a juggler walking forwards, and it's sort of like a multiple exposure photograph, but in 3 dimensions, this is what you would see. You would see this braid of 3 strands. If you think a little bit about this, if it was only the balls that were moving, then the 3 strands would be, they would fall apart. They wouldn't be connected to each other. And so I've also added in the positions of your 2 hands as you juggle them, which allows it to be connected together. This is a similar idea for a single juggling club. So the path of a juggling club as it's thrown from one hand to the other. And this is a combination of those 2 ideas together, 3 clubs being juggled, spinning through the air. And you get these this comes up in my work quite a lot. I do something for a purely mathematical reason, and then it happens to have a result which reminds you of something else. Maybe this looks like the wings of a bird. It's not intentional, but it's just a happy accident when it happens. More topological, a very common subject in topology is knots. So a knot, just as in a knot in a piece of string, except the topological version, you don't want any ends to the string, you want it to be a closed loop. So this is an example called the trefoil loop, or the trefoil knot. And this is a very special shape for this knot, which has an interesting property, which I'll show you here. So this knot rolls. So if you just imagine some sort of loop in space, probably when you lay it down on the table, it's going to find 3 points which it's stable on, and it's not going to be able to roll. And this particular shape, this particular shape has the property that wherever you lay it down, it never has 3 points in contact, and so it can always roll. And there's actually an open problem in mathematics. Which knots have this property? Which knots have a shape for which you can do this? So talking about rolling objects, this is a joint project with Lee Braswell, who's in the theater department at Oklahoma State, and who is interested in circus equipment. So he does rigging for shows, and he's interested in, there's a class of circus performance apparatus which consists of a big metal shape that you get inside of and you roll. And so there's a story behind this, which I won't get into because of the time, of this allows you to roll along and choose paths. I've actually got a video. This is Chris Delgado, who's one of the top performers in this class of apparatus. And I'm not as good as him, so I didn't want to show you me trying to do this. this is Chris experimenting with the shape.
Right backwards.
And I'll just play that again. And the shape allows him to choose a different path as he's rolling. So the rails are arranged in such a way that he can sort of change paths. Similar sort of idea, but using a different addition to 3D printing. So this is one of the things I like to do with 3D printing, to distinguish it from, say, computer animation, is that with 3D printing you can use other aspects of the real world. In this case, soap films. So this is illustrating the mathematical area called minimal surfaces, which soap films are a physical example of these things. The soap film tries to sort of pull as tight as possible to get a shape which takes up as the minimal amount of area, but keeps the boundary fixed to this shape here. So this is the knot from before, the rolling knot. If you dip this in soap film and you choose the correct, you have to pop some bubbles somewhere, then you get this beautiful surface which sort of twists in between the loops of the knot. This is actually something called a ciphered surface, which is something that topologists study. A ciphered surface is a surface whose boundary is a particular knot. And so this is the ciphered surface on the Trifle Knot, which you can make with soap directly. You can also make more complicated versions of this. As with a lot of mathematics, maybe it started out talking about something in the real world, but then it sort of expanded out into its own investigation. These are also shapes of ciphered surfaces. They cannot be made with soap film, unfortunately. Well, at least I think it would be very difficult to get these to be made with soap film, but you can still work out what the shape should be. So I did some work with an artist called Marco Mahler. Marco makes mobiles, so these kinds of structures, but usually he's working at a very large scale, big metal, kinetic sculptures for hotel lobbies and so on. And so we collaborated on making these 3D printed mobiles, and there's some interesting mathematics in here. So how do you work out where to balance, where do you put the hook on this beam here so that the weight of everything else here is balanced by the weight here? You can work these things out with your mathematics within your 3D design program. Here are some other examples. These are a binary tree, a ternary tree, and a quaternary tree. So if you're a computer scientist, maybe you're most interested in the binary tree, but these other ones are interesting as well. If you look at the bottom of the ternary tree, then you see Sierpinski triangles, one of these famous fractals. I want to show you another way to show fractals, and I need to show you just a couple of things to lead up to it. So here I'm going to start with just a line segment, and then I'm going to put a wiggle in it, and more wiggles, and more wiggles, and more wiggles. And this is a process that generates something called a space-filling curve. So if you keep doing this forever, then at the end you're going to get a shape where this curve completely fills in a two-dimensional shape. And so usually when you see these kinds of things, you see it as an animation through time, and instead you can animate through space. And so, so this is starting off with a straight line and then sort of continuously going through, getting more and more squiggly as we go down. So here's a large 3D print of this. We decided to display this with a mirror underneath, so you could simultaneously see the intricate curve on the bottom, and you can see the sort of how it got there. And these are a few more examples with different curves and the different ways in which they extend. I was saying before about sometimes people see something else in the mathematical work that wasn't there as I was designing it, but they interpret it some other way. I like somebody described this as a skyscraper going for a walk. Just decided to take off somehow. So this was an interesting project. This was with my brother, Will Segerman. He designs computer game characters. This is one of the things he does. And so he designed this monkey for me, and then I arranged it in such a way that it was showing a particular kind of symmetry. I won't get into exactly what's going on here, but this is a symmetry that only really exists in four-dimensional space. And so we have to do various projections to get it down into three-dimensional space. Here is some sort of variance. This one has 24 monkeys. This one has 120 monkeys. Now let me see if I can switch over and show you the animated version of this. So I'm going to have to put the microphone down for a second. Which is showing the symmetry. Every few seconds, one of say this monkey becomes this monkey, and that's showing this sort of symmetry. And if you press different keys on the simulation, then you can get the other versions of these animations. So let's go back to the talk. So what makes a good visualization? What makes something effective about this? Can we get the lights down for this, please? So I'm going to show you I think maybe one of the most effective visualizations that I've made. I'm again going to have to put this microphone down, so hopefully you can hear me. Casting a shadow of what it looks like, but something surprising happens when I put the flashlight exactly in the right place, is that this curvy grid is revealed to actually be, if I can get it in the right place, a perfectly regular square grid. Lights up again. So, well, here's a much better picture of the same thing. So I can't resist to tell you what the mathematics is behind this because it's so beautiful. So this is an illustration of something called stereographic projection. Stereographic projection is a map from a sphere to the plane. And the light rays do this stereographic projection. You can also write down an equation. It's not so difficult to write down a formula for this. But you can see exactly what is going on without needing to know any formulas or any equations, just by knowing that the light ray comes down and hits the sphere, and then it continues down and hits the plane. And that's what stereographic projection is. This was known to the Greeks. The very first maps of the stars were sometimes drawn using this method. And so what's so effective about this? I think there's a few things. First, it's sort of, there's a surprise, right? When I showed you the sphere, it's not at all obvious that what's going on, that there's a square grid in there. And then also, it's not a computer-generated thing. It's not a computer animation. If it's a computer animation, people know now you can do all kinds of strange things with computer animation. You can cheat. You can maybe be showing something that isn't really true. This is a piece of plastic and a flashlight. Everybody knows exactly what plastic and flashlights do, and yet it does this surprising thing. And of course, the mathematics is correct. That's also very important. If you're going to illustrate something and you want to tell a story about it as accurately as possible, whatever you're doing has to be correct. So here are a few variants of that same idea using different patterns. And there's lots of properties, beautiful properties of stereographic projection that you can talk about using these. These are examples which are relating to hyperbolic geometry. If people have heard of the hyperbolic plane. Maybe you've seen these, there were these Escher prints. Angels and Demons is a very famous Escher print, which is drawn on something called the Poincaré disk model of the hyperbolic plane. And one of the shadows of this is the Poincaré disk model, and then there are others. This is something called the Klein model, and the upper half plane model. This one 3D print sort of illustrates the relations between all three of those. Last summer in Edinburgh, a few of us had an exhibition which was all based around this idea of stereographic projection. So this is a globe which is projecting via stereographic projection onto a wall. This one is what I showed you earlier, but it's huge. It's 4 meters across and 4 meters tall. Various tilings. This was, so let me tell you about this. This was the last thing in that exhibition. So this is a zoetrope. So a zoetrope was sort of very early form of video movies. Maybe you've seen this as sort of a cylinder with slits cut in the side, and it would spin around, and you would be only, as you look through the slits, you only see each picture on the other side of the cylinder very briefly, and that was the first way that people tried to make movies. This is a similar sort of idea, except that these are three-dimensional objects that are on this rotating plate, and there's a strobe light, which is going off at precisely the right time, so that it shows you each of the models in succession. And I should make clear, 3D prints are made of solid plastic. They don't deform like this. This is an illusion of this spinning disk with the strobe light. And this is illustrating a rotation of an object in 4 dimensions. And it's being projected down to 3-dimensional space so we can see it. Now, it is possible to have 3D prints that do interesting things and move. Again, the previous one was an illusion. This is real. These are 3 gears which are sort of rotating through each other in this sort of complicated way. And again, this is one of the things I think using the medium that you're working in is very important. 3D prints, if you animate it, it's doing something real. If you animate some sort of computer animation, then, well, who knows if it could really work or not. If it's a real physical thing, then it really works. So there's a still picture of the same thing. And let me just because it's funny, let me tell you one story of where this came from. So I grew up in Manchester, and this was on a bus stop. And the idea here was that there were 3 different transportation systems that were going to come together and make the city flow beautifully. But if you think a little bit about what's going on here, if this gear rotates like this, then this gear has to rotate like this, and this gear cannot move. So in fact, these 3 transportation systems cause gridlock, nothing can move. And over here, the teachers, the students, and the parents come together, and nothing happens, nothing moves. So there's a challenge there. How do you have 3 gears which together, each pair meshes together, and yet it can move? And so this was one solution. Here's another kind of solution, this time with 4 gears, or 4, I guess these are racks rather than gears. So they translate, they're moving in a straight line rather than rotating. It's a similar sort of idea. I've got many of these things, again, are down on the table, and please come and play with them to explore them yourself. I guess this is another point. The videos are great, the 2-dimensional images are great, but these you can actually hold in your hands, and that gives you an extra little bit of experience of what the idea is. This is a very recent, this was a couple of weeks ago. This one is 5 different racks which are sliding through each other. You hear the sound on that one as well. So more things that move. This is an example of, this is showing something from topology. This is the torus, or actually topology and geometry. So the torus is the sort of donut shape. And usually when you see it, it's sort of curved on the outside with positive curvature, and it's curved on the inside with negative curvature. And this is an example which is actually flat. You can open it out flat onto the plane, which is the geometry that the torus really should have. And these are some puzzle pieces which are based on one of the 4-dimensional polyhedra. So like this is sort of, in some sense, this is like the 4-dimensional dodecahedron. Breaks apart into puzzle pieces. I've got very interested in mechanisms that expand linkages. So this is a sort of expanding structures. If you pull on all sides, it gets bigger. The name for this is auxetic. These are auxetic mechanisms. Here's an example, another example of a cube that gets larger when you pull on it. Dodecahedron. So we're actually in the process of getting these mass-produced. And this is maybe my favorite. This is based on the crystal structure of diamond expands in this huge. So, and there's maybe applications in, for example, in space. So in space, you go up in a rocket, you want a very compact thing that will fit inside of your rocket. But then maybe once you're in orbit, you want a much larger thing. And so these kinds of things can do this. So, so seeing all of these things is very well, but I think most educators would agree that just watching something happen is nowhere near as effective as doing it yourself. And so to that end, at Oklahoma State, we have a lab in the mathematics department that has some 3D printers. And I run a course every year where the students, well, so it's sort of a capstone course. So the students have taken lots of exams in mathematics, but they haven't really applied their skills and their knowledge to real projects. And so their homeworks are to design a parametric curve in space, and they have these or a fractal, or some sort of polyhedron, another kind of fractal. And so this is a good one. This is so this was a roller, so like a cookie roller. So there's a cylinder with a pattern, and you roll the cylinder over. This is Play-Doh, but you could do it with something else, and you produce a repeating pattern by what comes from the pattern that's printed on the roller. And just some more of the examples of the things that my students did. It's been really successful, and I think they really get into it. They get invested in an idea before they realize how hard it's going to be. And the mathematics is not necessarily going to be as simple as the things that you see in the exam. You have to get out there in the real world and discover that things are not as neat and tidy as it's often made out in your homeworks or your exams. And this is just a great quote from George Hart. The more math you know, the more stuff you can make. It's absolutely true. So I'm going to move on from 3D printing. I'm just very briefly going to show you something in virtual reality. And then we'll finish with talking about some spherical video, and I'll spend quite a bit more time on that. So, so this is just one example of something that I've worked on in virtual reality. Let me show you this video. And maybe I'll mute this.
Well, so let's see. I'm going to go around and see how many cubes there are.
So, so just as that's playing, I'll just talk a little bit about what's going on here. So this is a simulation of three-dimensional hyperbolic space. So what I'm seeing in there is not Euclidean space, it's hyperbolic space, whatever that means. So one of the features of this is that angles don't add up the way that you think they should do. So I walked around these squares. Each of these squares is the same size as the rooms that I'm going into here, but I had to walk around through six rooms to get back to where I started in the virtual space. Now, let me just maybe play that again.
Well, so let's see. I'm going to go around and see how many cubes there are. So I'm in the...
So we start in the black room, and then I go forward into the blue room, and then the green room. And what's going on here is that there are actually 6 rooms around that vertical pillar to my left. Here I am. If this were Euclidean space, I would be coming back to the black room, but I'm not. I'm in a yellow room, and I have to go 2 times further to get back to the black room. So this is you know, a simulation of something that cannot exist in the real world. There's no way you can do this for real, but you can get some of the ideas of this, and this is really using virtual reality. Again, the medium should be used to express something that you couldn't do in any other medium. And there's no way you can do this in a theme park or something like that. You have to do this virtually. Okay, so now let me tell you about spherical video. This is a whole other area of things that I've worked on. So this is a, maybe you haven't heard of this technology before. This is a spherical video camera, or it also does still pictures. So the way that it works is it has a fisheye lens on both sides and binds those 2 images together to give a view. So this is a photograph I took of this room earlier today. It looks kind of distorted, and the reason for this is that the whole sphere of data needs to be sort of squished down into a rectangle for storage on the computer and so on. So what I can do is I can show you what it looks like this way. So this is what it looks like in the viewer for this camera. So I was standing right there, and well, you can see that my hand is down there, so I actually had a very long selfie stick. And on the top of it was the camera, and you can see that I'm taking the photograph. You can do this with your smartphone. So that took the picture. And then you can look all around. And so this entire sphere of data was unwrapped onto the flat rectangle to get it onto onto this picture.
So this is a little bit like map making. This isn't the same as say the Mercator projection of the world. The Mercator projection actually sort of goes up and down, actually infinitely far if you think about it. This is just the angle. So the x-axis is just the angle around the sphere, and the y-axis is just the angle up to the North Pole and down. So I got interested in this for transformations. So what are the interesting transformations that you can do using a sphere of data rather than an ordinary photograph, or these cameras that are recording us now, they produce a flat image. So this is a photograph that I took at, so there's a conference called the Bridges Conference. It's bridges between the mathematics and the arts. It's a big annual conference. This was, I think in 2016 in Finland, there was a conference. And this was the conference photograph. So you can see I'm up there standing on this staircase, and again, you can't see the selfie stick that I'm holding, but it points out into the space, and there were lots of people below and lots of people above. And I've done some sort of unwrapping transformation. In fact, the transformation I used here was again stereographic projection, which takes the sphere of data and wraps it out onto the plane so that we can see everybody at once. So let me play you this video here. So this is me with two friends at Stanford University, and we're all jugglers. And this is the unwrapped. It's called the Equirectangular Projection, is what it's called. So again, so up at the top, maybe you can see there's a sort of stretched out lamp. There's a lamp up there that's got very stretched out because up near the top, all of the angles sort of come together. And down at the bottom, you can see here, this down here is the bottom of a tripod. There's some cork or something which the tripod sits on. And we're standing in a triangle around this and juggling. So let me actually switch out of this so I can show you which way is it? It's over here. So this is what the same video looks like sort of from the inside. It looks a lot more sort of normal. Well, maybe it's not that normal because there's 3 jugglers around you, but other than that. So this is one thing you can do. And now here's the same video, but we've transformed this somehow. So now instead of there being 3 jugglers, there are 6 jugglers. And everything still works out. So what's going on here? Oh, and there are also 2 lamps, right? So everything kind of got untwisted and doubled up. So just very briefly, what's going on here? Just give me 20 seconds of being slightly technical for people who might enjoy this. So the sphere of data gets projected onto the plane using the stereographic projection idea. And then we think of the plane as the complex numbers. And one of the things you can do with the complex numbers is you can multiply them together. So this is the result of squaring every pixel's location and then putting it back up on the sphere. And the squaring has this sort of doubling effect. So we had a lot of fun with this. Let's see, what else do I have here? So this is, I'll leave the sound on. A past version of me. So, as I was saying, my name is Henry Segerman. This is a spherical Droster video. So you're sort of slowly zooming this way, or rather the frame here is coming over you this way, and over there there's this sort of weird pedal portal in the middle of my apartment. This is the future, so there's future versions of me over there, and this is the past. So I'll hand you off to a past version of me to explain again what's going on. A past version of me. So, as I was saying, my name is Henry Segerman. This is a spherical... I'll spare you seeing that again. So this is using... well, we saw the squaring effect. So I actually got interested in these questions or this spherical video for a different reason, which was thinking about the question of what does zoom mean for a spherical video? So for a flat video, what does it mean to zoom into the video? Well, it's flat. You just scale it up, and then you crop your frame in so that you're seeing less of it, but it's bigger. And what is the right way to do that when you have a sphere of data? There is no frame, so there's nothing you can crop, but there's still a sensible notion of zoom. And, well, so this is inside of the spherical viewer, so you can look around and see what's going on. And so, yeah, so this uses this spherical notion of zoom, which is based on something called Mobius transformations to do this effect.
So you're sort of slowly zooming this way.
Let's see, what's the next one that I have? Oh yeah, so this is another interesting experiment. Actually, maybe I'll play this in the other viewer. It's sort of complicated doing a talk with two sets of slides. That one spherical set of slides and one non-spherical set of slides. So what's going on here? I'm walking around a room, and you can see that things are distorting in a sort of strange way. So this is maybe, if people are familiar with, there's an effect in film called the Dolly Zoom. So this is where, in flat film, so this is where you're focused on some subject, and you simultaneously roll the camera towards them whilst zooming out. And so what happens is that the person doesn't change much in size or shape, but the world around them distorts in a strange way. So what's actually going on here is that there are three markers on the wall. So there's this blue marker here, and a red marker here, and a pink marker here. And what's happening is, this is sort of like a stabilization effect, that as the camera is moved around, we modify the view. We move it, again, by these Mobius transformations in such a way that these three markers always stay in the same place. Okay. I think I've got one last... I've got a couple more things. I'm gonna let this play for a little bit. This is joint work with Vihart, who is, you may know from her YouTube work. She's doodling in math class. And this is a combination of, well, you'll just see. This is using the musical form of a round, where there's a number of people singing the same thing but offset in time, with these sorts of tricks again. So what's going on here, let me try and explain what's happening and talk over the beautiful music, I'm sorry. So there are three pianos. Well, there's a triple piano, but there are three different sets of piano keys, and they're offset in time by 20 seconds each. So Vi is singing one of the three parts of the round here, one of the three parts of the round here, and one of the three parts of the round here. And so usually in a round you would have three singers who would be singing the different parts. Here there's only one singer, but we've made copies of her. And then we're also doing some sort of complicated things, interacting with each other. So the sheet music, you'll notice, there's only one copy of the sheet music. There are three copies of Vi, and there are two copies of me. And so Vi puts the sheet music on her neighbor's music stand, come back over here, and then the next Vi picks up that sheet music, plays a couple of notes, gives it to me, I pass it back to her, and she puts it on the music stand for the next version of Vi around. So there was some sort of trickery with standard sort of movie cloning parts, and this tripling effect. So I showed you the squaring effect, where there were two copies of the jugglers. Here it's using Z cubed. There are three copies of all of the piano players, but then there's many more confusing things going on here. There's a lot to think about here, but maybe I won't spend more time on this. So I'm almost done. I guess there's only a couple of things more to say. So, so I have a book, it's down here on the table, it's called Visualizing Mathematics with 3D Printing. Let me just tell you a little bit about it. So, so this is a popular mathematics book. It should be hopefully accessible to lots of people. I mean, I wrote it to be accessible to everybody, but I'm not sure I succeeded. And sort of the idea of the book is that it uses photographs of 3D prints for all of the figures, almost all of the figures. And all of these 3D prints are linked on the website. So, so there's a chapter on polyhedra, say. And so if you click through to, so this is the figure 2.9 in the book. And on the website, there's a 3D model that you can experience on your computer or on your phone. And the idea somehow is that if you want to talk about 3D content, then having a flat image in a book is not so effective. That really what you should be doing is having a three-dimensional figure to explain your three-dimensional ideas. And so here you can explore this virtual figure, or even better, you can print out your own. You can order these things on Shapeways. Here's a video. Shapeways is the company that I use to make all of my 3D prints. Here's a video of where I explain something about what's going on here. And there's also a link on Thingiverse. Thingiverse is a repository of 3D files, and so you can download these the 3D file for this so that you can print it out on your own printer and maybe have a shelf full of these 3D prints so that when you read the book, you can look at the figure with your own eyes and hold it with your hands. So, with that, I think I'm done. I'm on Twitter, I'm on Instagram. This is the webpage for the book. This is my webpage. I'm on YouTube. There's lots and lots of videos of all of these things. Shapeways is the company that makes my 3D prints, and Thingiverse is where you can download all of these 3D prints. So thank you very much for your attention.